Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. In my video on the Feedline Side of the antenna tuner, I said that I had performed a mathematical experiment to determine the various power levels and, ultimately, the total loss due to both the matched loss of the feed line and the effects of SWR. This video is in response to a request for a video on the mathematical process I followed to do this. Thus, in this video, I will present three methods of determining the total loss associated with a given antenna system with a known SWR and characteristic loss of the feed line. The third method is the one that I used for my video. Now, to be sure, there's nothing complicated about the math. It is not beyond the beginning 9th grade algebra student. I've provided a link in the description to a formula sheet which contains all of the equations in this video. I also put a link in the description to a zip file which contains the Excel spreadsheet that I used for the third method that I will cover in this video. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. Now, I'm going to begin with mapping out the path. As I said, I'm going to be presenting three ways that you could approach this analysis. Regardless of which way you choose to go about it, you will need certain information to move forward. You will need to know the matched loss, or this is the loss in dB when the feed line is matched. This is the loss of the feed line that you might find on its data sheet for the frequency in question, or what you measured using your antenna analyzer or VNA. I will call this L sub m in keeping with my 1984 antenna book published by the ARRL. You will also need the SWR of the antenna at the antenna. I will call this S sub L in keeping with my antenna book. Now, if all you know is the SWR measured at the transmitter, then this is not the same as what exists at the antenna itself. I will call the SWR at the tuner end of the feed line S sub I. We can calculate the SWR as seen at the antenna using, well, this lovely formula from my antenna book. Oh, don't let this scare you off. Notice the repetition of terms with only the difference being that we add stuff in the numerator and subtract stuff in the denominator. We'll take it one small piece at a time and then put the results of the small pieces together in the equation. So let's do an example to see what I mean. I measured the SWR at the tuner end of the feed line as 3.3 to 1. I measured my feed line loss at 0.5 dB of attenuation. So I'll start with the first piece. The first piece is SI plus 1 divided by SI minus 1. So that gives us 3.3 plus 1 divided by 3.3 minus 1. The resulting value is 1.870. Now the second piece, that is the 10 brought to the L sub m over 10 power. That gives us 10 brought to the 0.5 divided by 10, which gives us a value of 1.122. Now, let's put it together to get the SWR at the antenna itself. So, the SWR at the antenna itself, SL, is equal to, on the top we have 1.870 plus 1.122. On the bottom, we have 1.870 minus 1.122, which gives us a value of 4.00 to 1. This then would be the number that we would use in our calculations from here. If you want to know how much power is actually getting to the antenna, then there's one more piece of data that you'll need. You will need the output power from the transmitter. Let's call this P sub XMTR. Now, let's move on to the three methods, starting with the simplest. Well, the first method is the easiest method, but it is also the least precise. This will require you to either procure an antenna book from the ARRL or a copy of Walter Maxwell's book, Relfections. In my 1984 antenna book, there is a graph on page 3-12, figure 23. This graph goes all the way back to the 1964 antenna book that my Elmer gave me in eons past, and, well, probably a long time before that. What you see here is the one that I scanned for my 2019 copy of the antenna book from the ARRL, page 23.13, figure 23.15a. So, how do we use this thing? Well, the horizontal axis is the matched loss of the feed line. The various curves that you see on the graph are the SWRs as measured at the antenna. We know the SWR at the antenna end of the feed line either because we measured it or we calculated it using the equation I spoke of. So let's walk through our example. First, we locate the curve which is associated with an SWR of 4.0 to 1 at the load. Next, we locate the vertical line which is associated with the 0.5 dB of the feed line's matched loss. Now we place a dot at the place where the SWR curve and the matched loss line cross. Next, we draw a horizontal line from this crossing point to the vertical axis on the left side of the graph. Now we can use our calibrated eyeball to read the additional loss in dB that we incur due to the SWR and the line loss. I see 0.47 dB. The total loss is now equal to the feed line's matched loss plus this number that we read off of the chart. This will give us a total loss of 0.5 dB, that's our matched loss, plus 0.47 dB, that's our additional loss, which gives us a total loss of 0.97 dB. I'm going to call this loss subtotal. With an S unit being 6 dB, this amounts to less than 1/6 of an S unit. And this is pretty insignificant. But you ask, how much power is actually getting to the antenna? Well, we use this formula. The power going to the antenna is equal to the power of the transmitter times 10 brought to the minus loss total over 10 power. So now we bring in the power provided by the transmitter. Well, in this example, let's assume this is 100 watts. Now, let's calculate the power actually getting to the antenna. The power getting to the antenna is 100, that's the transmitter power, times 10 brought to the minus 0.97, this is the total loss, over 10 power, which gives us the power going to the antenna of 79.98 watts. So what is this method number 2? Well, method 2 consists of a mathematical calculation using the formulas provided in my 1984 antenna book. Now, before I show you the equation, remember that there are actually only 2 pieces that we have to be concerned about. And so we will work through this one piece at a time and then put it together to get the final number. Now that you're warned, here is the equation. Okay, I know. Look at that thing. Well, let's work through this together. Now, there are 2 core components, like I said. The first I will call B, and it is equal to 10 brought to the LM over 10 power. Remember, LM is our matched loss of our feed line. And we know the matched loss of our feed line is 0.5 dB. Putting this into the equation, we get that B is equal to 10 brought to the 0.5 divided by 10, which gives us a value of 1.122. The second I will call C, and it is equal to the SWR at the antenna minus 1 divided by the SWR at the antenna plus 1. And we know our SWR at the antenna is equal to 4, and so putting this into this equation, we get that C is equal to 4 minus 1 divided by 4 plus 1, giving us a value of 0.6. Now, we can go back to our monster equation and put these values into it. So we get that the total loss is equal to 10 times the log to the base 10 of this big mass. We got 1.122 squared minus 0.6 squared divided by 1.122 times the quantity 1 minus 0.6 squared. And working all down through this one piece at a time, we end up coming down to a total loss of 0.97 dB. And this is the same result that we got using the chart in method 1. Now we follow the same path to find the power actually delivered to the antenna. Now on to method 3. Well, method 3 is the one that I use for my video because, well, it gave me an inside look into the process. This required two equations. The first is a simple equation which simply answers the question, how much power am I getting out when I put so much in and have this much loss? And it looks like this. Power out is equal to power in times 10 brought to the minus loss over 10 power, where the loss is expressed in dB. The second equation answers the question, how much of my forward power is being reflected when I have an SWR of the antenna at S sub L? This one looks like reflected power is equal to the forward power times the squared quantity of the SWR at the load minus 1 divided by the SWR at the load plus 1. Now, let's walk through one trip. Trip 1 begins when the transmitter's 100 watts starts moving toward the antenna from the tuner. It is attenuated by 0.5 dB on its way to the antenna because of the matched loss of the feed line. The power that arrives at the antenna is equal to 100 times 10 brought to the minus 0.5 over 10 power. And that amounts to 89.125 watts. Now we have an SWR at the antenna of 4:1, so we have reflected power equal to 89.125 times the squared quantity of 4 minus 1 divided by 4 plus 1, which gives us a reflected power of 32.085 watts. The power delivered to the antenna is equal to the forward power minus the reflected power. So that is 89.125 minus 32.085, which gives power to the antenna of 57.04 watts. But the reflected power suffers from the same loss on the way back to the tuner as the forward power did on its way to the antenna. And so it emerges at the tuner as 32.085 times 10 brought to the minus 0.5 over 10 power, with 28.596 watts arriving at the tuner from the antenna. Well, this gets added to the transmitter's 100 watts, giving us 128.596 watts starting trip 2 as it travels back toward the antenna. This process repeats over and over and over again, but it does come to an equilibrium after a few cycles. In the end, we get 79.883 watts being delivered to the antenna. This amounts to a total loss equal to minus 10 times the log to the base 10 of the power being delivered to the antenna divided by the power that the transmitter is putting out. So that gives us minus 10 times the log to the base 10 of 79.883 divided by 100, which works out to be 0.975 dB. Wow. Now, you'll find all of this in the spreadsheet that I have provided. So there's the math associated with the whole thing. If you found this video helpful, please click on the like and subscribe. Thank you so much for watching. Until next time, Toodle-Oots.